Hello everyone! In this tutorial we are going to learn how to simulate a state-space model of a dynamical system in C++, and we are going to use the Eigen matrix library. We are going to focus on discrete-time state-space models. You can obtain these state-space models by discretizing a continuous state-space model using, for example, a backward Euler method. Why I'm making a special video and tutorial about this topic? Well, simulation of a dynamical system or a state space model is an essential step for developing control algorithms or just by checking the stability of a system. So that's why I'm focusing on the whole procedure. I want to explain you the complete procedure, a discipline actually procedure for simulating a dynamical system in C++. But we are not going only to simulate a system in C++. We are actually going to build a class such that you can use this class in your other projects. That's the power of C++, this object-oriented design that you are going to see in this video. As always, I created a post that accompanies this video, and everything that I will explain in this video is actually nicely summarized, and the link to the post is given in the description below. So if you don't have time to watch this video, you can always read the post. Let us first explain what does it mean to simulate a state space model of a dynamical system. In this video, we're going to consider systems living in discrete time. So the discrete time state space description has the following form. Now, the main question is, how is this state space model related to the classical state space model in continuous time? That's the main question. By using a backward Euler method, you can transform or you can approximate this continuous time state space model by a discrete time state space model that is much more convenient for simulations. So how to do that? So the idea is to approximate the state vector using backward differences. So you can write down x dot is approximately equal to xk minus 1 divided by h. Now, what is this k discrete time instant? How can we visualize it? Well, if you have a trajectory in continuous time, so let's say this is your continuous time trajectory, you're discretizing basically by introducing these finite differences. You're discretizing this trajectory and you're looking at the vectors in discrete time, where the distance between the time distance between two variables will be h. This is your discretization step that you are basically choosing it. It's a user choice. And you're looking at the system behavior at kh, so this will be the time kh, and this will be k plus 1 times h. Now, for simplicity, we don't want to have kh here, so we just represent this state vector as xk and this one as xk plus 1. Now, using the backward Euler method, you can transform the continuous time system in the discrete time system, and the procedure is super easy. You just can, based on the basis of this transformation or this approximation, you can simply write this equation. And you can manipulate the first equation, right? You can manipulate the first equation. You can write it down as follows. You can basically say that this equation is equal to and then you can put this term on the left hand side and you can obtain identity minus h, capital H, xk is equal to xk minus 1 plus HLUK, and then you can simply invert this matrix, which is not recommended for large-scale systems, but for systems having, let's say, 100 state order, that's fine. You will obtain the following representation. And now, by comparing this StateSpace model with this StateSpace model, you will obtain that this is A, this is your B matrix. The C matrix remains unchanged since you don't manipulate the output equation. The only issue that we are having here is that the time vector in this approximate equation is k, and in the original equation this will correspond to k minus 1, because you can see here that this is just propagated in time, that in this original system state is propagated in time. Well, you can simply, with the small approximation error, you can replace this by the xk minus 1. Okay, and this is the procedure for transforming your continuous times models into discrete time models. There are many ways for simulating this system in C++. You can define functions, you can, in your int main function, you can define certain code that can perform the steps. However, this is not a disciplined approach. Instead, I'm going to follow a more disciplined approach for simulating the system. This approach relies on object-oriented design and relies on classes. So I'm going to define a class called simulate system, and this class, by calling its actually member function, I'm going to perform simulation. I will be able to save my data into a comma separated value file. I will be able to open the data from a file, and I will be able to do some other steps. Why do I choose this step? Well, I want to make sure that I can use this class in my other projects. Now, here it's very important to emphasize that this piece of code is necessary for developing more advanced controllers, or for checking the system stability, or performing many other steps. That's why I have dedicated a complete video to this problem. So let us explain this class. We have a simulate system class. Class simulate system. This class should contain as private member functions. Definitely, it should contain our system matrices A, B, C. Then it should contain the initial state. What else this class should contain as private members or private member variables? We need to have input simulation sequence. So the input sequence that we are going to use for simulation. Let us elaborate a little bit more how this input sequence is being constructed. Well, this input sequence is actually a matrix. Every entry or actually to be more precise, every column of this input sequence is the input vector at discrete time, at the corresponding discrete time. So the first column vector is u0, the second one is u1, and the last one is un, where your n, or actually n plus 1, is the total simulation time. Of course, we're talking about discrete time. So this will be also a private member. And when we construct the object, simulate system object, we will specify these variables. Then, our simulate system function should also contain the results of our simulations, that will be the state sequence. Then, we should have also the output sequence. What else should we have? We should have as private member functions the dimensions of the system matrices. This is maybe a little bit redundant. However, I like to specify everything such that some other people can easily read my code. So the A matrix has dimensions n by n. B matrix has a dimension of n times m, and your C matrix has a dimension of r times n, where n is the state dimension, your m is the input dimension, input vector dimension, and your r is the output dimension. So you can specify as private members n, m, r. Then you also need to specify the total number of samples, n plus 1, right? Or you can just simply specify n as your private member, and you can also define simulation time vector. Time vector. So this simulation time vector will actually contain all the discrete time steps. It will contain the entry 0, 1, 2, 3, etc. until n plus 1. Let us now explain the class constructors and the overloaded constructors. Definitely, I would like to provide a default constructor. In my case, this default constructor should set all the variables to one-dimensional matrices and set all the variables to 0. All actually matrix entries to 0 matrices, one-dimensional, and all the scalar variables to 0. So let us look into the implementation of this constructor. So this is our default constructor. I'm using Eigen C++ matrix library, and here I assume that you watched one of my previous video that introduces the Eigen matrix library. The link is also provided in the description below. So here I set the n, m, n, and r private member variables to 0. Here are actually our private member variables. Here's how they're defined. These are the matrices A, B, and C. This is basically the x0 initial state. Notice this notation. This is the Eigen C++ notation. And this means a dynamic matrix. That means that the matrix whose dimensions are determined at runtime. And this D denotes basically double. So all the variables are double. This is our input sequence. This is our simulated state sequence and simulated output sequence that are used to, that are actually products of our simulations. They are computed by the class member functions. We are going to introduce these member functions. Here is our row vector, time row vector containing entries 0, 1, 2 until the simulation time, or time samples. We call the simulation time samples. And here are dimensions of the matrices, and time sample is a basically scalar defining, or actually an integer scalar defining the total number of simulation steps. Okay, so this constructor, the original constructor or default constructor, should set all the entries to 0. Here is how we set the entries to 0. We need to resize the matrix. Okay, you set to 0, set to 0, set to 0, everything. Here, you repeat the procedure for all the member functions. So once I call or once I define a simulate system object, all the entries will be set to 0. So this was our default constructor. Now, we need to define an overloaded constructor such that we can define an object with certain simulation conditions, such that we can specify the simulation conditions. So let us look into this constructor. This is the second overloaded constructor, and let's look into its implementation. So this constructor takes as an input A matrix, B matrix, C matrix, defining your state space model. It specifies the initial state and the input sequence matrix. Input sequence matrix is this matrix, right? And notice that we do not specify here the number of simulation steps, the private member variable here, time samples. We don't specify it because this time sample variable is encoded in the number of columns of this matrix. Now, we simply assigned all the private variables, right? We extract the number of rows and columns. We extract the time samples, the number of columns of input sequence. Then we resize the simulated output sequence, the simulated state sequence according to input parameters. We simply resize them and set them to 0. Okay, and we fill in the time row vector with the entries 0, 1, 2 until time samples -1. Okay, so this was our simulate system overloaded constructor. Let's look into other functions. Now, I need to provide functions that will enable me to save and open the data. These functions are save data, and open from file. Since I want to keep this video relatively short, although this video will be more than half an hour, I have created another video that explains how these functions are being implemented. So these functions are basically loading and saving data, matrix data or Eigen objects into and from comma separated value files. Right. In this case, save data will take your basically the name of the file in which you want to store your A matrix, the name of the file in which you want to store your B matrix, the name of the file for C matrix, and for other important simulation results or parameters. So you're also saving the input sequence, simulated sequence, and you're also saving output sequence. So you're saving more or less all the private members into separate files, into comma separated files, such that you can interface this code with Matlab or with some other programming language. Now, this function open from file opens the data from comma separated files and converts the data into Eigen objects. So this function is heavily relying on open data function, and here is its implementations. I'm not going to comment these implementations. So this is the implementation of save data. This is the implementation of open data, right? Basically, open data reads the comma separated value file line by line. And this function is basically called by this member function, open from file. And in this function, you can specify source files, the string values of source files. Okay, now we have explained open save functionality of our code. There are actually 3 functions. What else do we need to explain? Well, or what else we need to add? We need to add the getter functions to get. Okay, get the data. We need the get data function, because in our code, when we want to plot some results or to perform some additional analysis, we want to extract certain private member variables or objects. So how to do that? Well, here's the function, get state output time. So this function returns a tuple. Okay, tuple, I'm not going to explain tuple in this video. Basically, it's a set of variables. You can define a set of variables, and the first variable will correspond to your state sequence, the second to the output sequence, and the third will correspond to time sequence. So you can extract private members from your class. This is the power of C++. The templates are the main power of C++, in my opinion. There are also other benefits of using C++. Speed of code, you can embed it, but I like templates. Okay, now we have constructor. We need an overloaded constructor, open and save functionality, and get data functionality. Finally, we need to provide the core of our class, and the core of the class is basically run simulation. So we need run simulation functionality. So this function will take A, B, C, X0, and input sequence. It will recursively compute your output vectors, and it will store these output vectors into your state sequence. Actually, first, I have to correct myself. This function will compute first state sequence and the output sequence, and it will store these sequences in state sequence and output sequence. So here is the implementation of run simulation. Notice the simplicity of the code. Notice how the code resembles the Matlab code, the equivalent Matlab code. It's very similar, and that's the power of Eigen C++ library. So here is what's going on. Since this function has an access to the private members, it just recursively computes the variables, starting from x0, right? And you're simply propagating your state equation. So this is our recursive propagation of state equation. So this is this equation implemented in C++. Okay, and you simply populate the simulated state sequence and the simulated output sequence. Okay, we have explained the main parts of our class. Now, we have to explain how to test this class, how to test the simulation, the run simulation function, and how to test the functions for saving and opening the data. Well, to perform the test, we need to have another programming language, and we need to perform the same operations using another programming language. So I decided to basically generate a random matrices, generate basically a random A, B, C matrices, input sequence, and initial conditions in Matlab. Then I'm saving these matrices into CSV files. I'm saving them, right? At the same time, I'm just going to simulate the system to see what kind of outputs I get. Okay, so if I run this code should produce simulation results for a system having 100 states, 10 inputs, and 10 outputs. And I'm plotting now the first output of the system that you can see over here. So it's a random response. Why it's a random response? Because the system itself, if you look in our original system, the input sequence is a random variable, right? The state is a random variable. The dynamics of A matrix is also of interest to check. We can check the eigenvalue of A. So here are the eigenvalues of your A matrix. It's quite undamped. The system is not damped. Notice that this is in discrete time system. Okay? And I'm simply saving the files into comma separated value forms. Then I'm going to load these files into my C++ code. So this is a driver code. This is a driver code for simulate system class, for demonstrating the capabilities and testing capabilities of the simulate system class. Notice here that I'm calling the default constructor, then I'm defining, or actually not defining, I'm basically calling the function open from file. I'm specifying A file, B file, C file, X0 file, and input file. These are the files produced by my Matlab code. Here are the files, right? So I'm loading this data into my C++ code. Then what I'm doing, I'm running the simulations. So I'm running the simulations, okay? This function, as I explained previously, will fill in the member functions, simulated state sequence, is simulated output sequence, will fill in this function. At the same time, I time my code just to check how faster or slower is my code compared to Matlab, right? This is very interesting to observe. And at the end, I'm saving the simulation data. So I'm saving all the data being produced by my C++ code in another file. So I'm saving A file output, B file output, C file output, right? Then I'm saving input sequence, right? Then the most important parts that I need to save is simulated state sequence and simulated output sequence. I'm saving them in CSV, comma separated value files. Then I made another Matlab script, and this Matlab script will open the outputs and state sequences produced by my C++ code. I'm going to open them, save them in output and state files. At the same time, I'm going to open A, B, C, X0, and input matrices or vectors that are used to generate the data, right? And I'm going to, for such A, B, and C, and X0 and input matrices and vectors, I'm going to simulate the system in Matlab. So this function over here is a Matlab equivalent of our run simulation function. So this function is equivalent to our Matlab function. So I'm going to perform all the operations in Matlab for specified initial state and input sequences. So the input sequences and initial condition are the same, both in my C++ code and Matlab code. And Matlab will produce its results. It will produce Matlab output sequence and Matlab state sequence. And then, as a final check, I'm going to plot the results. I'm going to plot the results produced by Matlab and plot the results produced by C++. I'm going to compare it graphically. I'm going to just look into the error. I'm going to plot the error between two simulations, and I'm going to plot or show the relative error between two matrices. The matrix produced by Matlab and the matrix produced by C++. Let's see what happens. Actually, I need first to run my code here. I'm going to build solution. Okay, hopefully no errors because I tested it a few times. Okay, and then I'm going to start without debugging. Okay, so nothing is being shown. The code runs, the code opens the data from CSV files, simulates the system, and save the data into CSV files. You get basically get 4,780 microseconds, right? You get below 1 millisecond for a system having 100 state variables. Let's see what Matlab produces. So let's see what do we get in Matlab. Okay, so we run the code, and what you can see here is probably, let's see, the black line should correspond to the C++ output sequence, one of the actually output sequence. You don't see the output sequence produced by Matlab. It should be plotted in red, you see over here. Where is it? Well, it's hidden behind. So there is a complete match between Matlab output sequence and the output sequence produced by our C++ code. Let's see the error. So we are plotting the error between the Matlab output and our C++ output. The error is in the order of 10 to the minus 15. This is very good. Okay, this is kind of machine precision almost. And then you get norm. Let's see the norm. Norm is very good. Okay. Then we can also do another check. We can check the state sequences. So we can check the state. Okay. We can check the state sequences and see what do we get. (10 to the minus 15). Very good, very encouraging. So our code works very well. Matlab produces similar results when we give to Matlab similar initial condition and state sequences. I'm going to post this codes, these two functions, on GitHub, and you also have my post. You can also look into my post. Everything is explained in my post, which can be found over here. I'm going to provide you a link to this post. Here I clicked on the post, so you can see the link over here. And I'm going to also provide you Matlab codes that you can play, you can modify it. Feel free to do all the modification you think it's necessary. Of course, this code needs to be improved. A lot of things can be improved over here. You can think of not storing, let's say, storing as references, storing member variables as pointers, playing a little bit with memory, because this code is probably not optimized for large-scale matrices. For example, this function returns by value, and we don't want that with large-scale matrices, so you would definitely give the pointers as the result or references. Of course, this function also for opening and saving the data can be improved, since I'm never basically checking exceptions. You can make this code to be more robust. In the future, I'm going to use this code to develop Kalman filter implementation in Eigen C++, then a linear quadratic regulator implementation. I'm going to probably code a Riccati equation, solution of the Riccati equation, and some other interesting control engineering topics. Definitely, I'm going to also implement system identification method in Eigen C++. Thank you very much for your attention. If you like this video, please subscribe or support this channel in some way. Have a nice day.